Hello viewers, in today's session I am going to discuss sodium potassium system. Outline of today's lecture will be, I will try to recapitulate what has been covered in the last session. I will tell you again what is paractic system, and the example we have that of sodium potassium system, and finally I will summarize what is a peritectic reaction. This refers to a case in which two components form a compound C that is unstable. When it is heated to high temperatures, before reaching its melting point, it decomposes to give rise to another solid and a melt having a composition different from that of the original compound. It is said to possess an incongruent melting point. Peritectic reaction can be represented as solid C. In this case, this is the solid which is unstable. When we try to heat it, before reaching the melting point, it decomposes to give a new solid, in this case B, and a melt. Solid C and the melt have different composition. This is a reversible process. Solid B and the melt, when cooled, they give back solid C. Let us now look at sodium potassium system. In this case, sodium and potassium have a tendency to form a compound with the formula Na2K. The compound is unstable at high temperature and decomposes before reaching its melting point. It is said to undergo a peritectic reaction. Compound Na2K has an incongruent melting point. General nature of the phase diagram of such systems has been discussed in earlier session. As I told you, sodium potassium system shows peritectic reaction. We can see here solid compound, that is Na2K, upon heating decomposes to give solid sodium plus melt. This melt has a composition different from that of solid compound. This is a reversible reaction. In this case, we can see the changes at the peritectic temperature, in which solid Na2K compound, being unstable, undergoes decomposition to give solid sodium and a melt having a different composition. In this figure, we can see the schematic phase diagram of sodium potassium system. This slide is familiar to you because this is the general behavior of all peritectic systems, and we can see in this the eutectic point as well as a peritectic reaction taking place at peritectic temperature. In fact, the diagram is not complete, but it is given in the book because there is a tendency for sodium and potassium to form a solid solution. If I ask you a question, do sodium and potassium form solid solution? The answer is yes, but they are not represented in the earlier phase diagram. Sodium and potassium are partially miscible in the solid state and completely miscible in the molten state. In the phase diagram presented earlier, that part was not traced. So, correct phase diagram should include the formation of solid solutions. Note this, the system involving solid solution formation in details will be covered in advanced course in phase equilibrium. Now, to give you a feeling, let us look at the phase diagram, complete phase diagram of sodium potassium system. You can note the difference between the earlier diagram and this diagram, especially on the two sides. You have regions corresponding to the formation of solid solution between sodium and potassium. This arises due to the partial miscibility. The system splits into two, one a sodium rich solid solution, the other potassium rich solid solution. On this end, you will see solid solution of sodium and potassium named SS1. On this end, you have the region corresponding to solid solution of potassium in sodium called SS2. Now, let us look at the systems when cooled give us different changes or transitions. Let us start with a melt corresponding to composition A, number of degrees of freedom being 2, cooling can be smooth, the temperature decreases, nothing happens otherwise till we reach the liquidus line here, at which the solid appears. In this case, solid solution 1 makes its appearance, number of phases become 2, number of degrees of freedom become 1. That means cooling can continue along this line. As the cooling continues, more and more of solid solution 1 comes out, and this process continues till we reach the eutectic temperature, at which third phase makes its appearance. In this case, it is solid Na2K. The system becomes a 3-phase system. As long as 3 phases coexist, the temperature will not decrease. That means when the molten mass is completely solidified, the number of phases remaining will be 2 and cooling can continue. Therefore, you have solid solution that is there and the eutectic at this point. Now, look at the changes that are taking place when we cool a melt corresponding to point B. Number of degrees of freedom being 2, cooling can easily be carried out. When we reach the liquidus, solid comes out, and the solid that comes out is solid solution 2. There are 2 phases. We are still left with 1 degree of freedom, so that cooling can continue. More and more of solid solution 2 comes out, and this continues till we reach the horizontal line corresponding to the peritectic temperature, at which another solid makes its appearance. In this case, the compound Na2K. The system becomes a 3-phase system. The temperature gets arrested because we don't have any degree of freedom. F becomes 0. The overall composition is such that the solid solution 2 disappears from the scene, and we are left with the compound Na2K plus the molten mass. And when that happens, cooling will continue down the line with the separation of more and more of Na2K, the compound. Finally, we reach the eutectic temperature, at which the system becomes a 3-phase system. We lose the degree of freedom. When entire molten mass gets frozen, we are left with only 2 solids, and they are solid Na2K and the eutectic. The cooling continues, and we end up with a solid of this composition. Now, let us look at what happens when we cool a melt corresponding to point C. The changes are almost similar to the earlier case, but at the peritectic temperature there will be some difference. We reach the liquidus, solid solution 2 appears, system becomes a 2-phase system, number of degrees of freedom 1, cooling can continue, more and more of solid solution 2 comes out till we reach the peritectic temperature, at which again it becomes a three-phase system. There will be a temperature arrest because F is equal to 0. When we try to cool the system, cooling and decrease in temperature can take place only when one of the phases disappears. In this case, the molten mass gets completely solidified because of the shift in the equilibrium of this reaction, and we are left with two solids, solid Na2K and solid solution 2. So, the phase diagram can be utilized to find out the changes that take place when a particular melt of a composition anywhere between 100% potassium to 100% sodium is taken. As I told you, the phase diagram for sodium potassium system, in addition to a eutectic point, exhibits an incongruent melting point, also called the transition temperature, meritectic or peritectic temperature. The various points and the regions of coexistence can be easily identified on the phase diagram once you become familiar with it. The melting points of sodium and potassium are 97.5 degrees centigrade and 63.0 degrees centigrade respectively. Other details are given here. The eutectic point corresponds to minus 12.5 degrees centigrade. The eutectic composition corresponds to sodium 0.5 mole fraction. At the eutectic point, there are number of phases 3, number of components being 2, number of degrees of freedom is 0. The compound Na2K shows an incongruent melting point at 6.6 degrees centigrade. The compound Na2K is unstable and decomposes at this temperature. The composition of the solid and the liquid phases is unequal. Hence, this is a peritectic reaction. Let me summarize what you have seen in today's session. I told you about the background information required to study sodium potassium phase diagram, that is the general features that are expected in a system showing incongruent melting point, that is showing a peritectic reaction. What is a peritectic system that we have seen? And finally, we looked at the sodium potassium system. I presented a phase diagram which is generally found in the textbook, which is not a detailed phase diagram, which does not include the formation of solid solution between sodium and potassium. It only showed the formation of a compound Na2K, which shows the peritectic reaction. That means it has an incongruent melting point. In order to give you complete information, I also gave you the complete phase diagram in which the formation of solid solution is shown. Although you have not been introduced to solid solutions, you will be studying such systems in the advanced courses of phase equilibrium. Nevertheless, this information is useful to you and it will help you to understand the phase diagram in toto. Thank you.